Of course. Okay, so where's my shared screen? Where's my Zoom shared screen? Oh, there it is. All right, there we go. Okay, so in this chapter, we did a bunch of different reactions, and what I want to do now is look at how to finish up, how to figure out where this Robinson annulation goes. Then I have one more related reaction we're going to talk about, which is the manic. And then after that, what I want to do is I want to go through and summarize the reactions of chapter 19, looking at what to look for in your starting materials and what to look for in your products, and you'll know which is which using that method of trying to identify starting materials and products and knowing which of the different reactions are which. Okay. So in the annulus, in the Robinson annulation here, we actually have 3 steps of the three different types of reactions we have here in this chapter. We do an addition reaction, a conjugate addition reaction first, and then we do an aldol addition reaction, and then we do the dehydration, the second half of the aldol condensation. So we're doing 3 of the same types of reactions, and it always forms a 6-membered ring. And when we talked about it on this slide here, we looked at exactly where do we break it apart, where do we chop it up and look for things, okay? So let me also show you the other way around. Once we have something that is, oops, hang on. There we go. Okay, once we have a substrate, let's make sure we line up our 2 reactants so that we get the correct product in the end. Okay, so that's what I'm going to show you now, okay? So the way what we want to think about drawing our Robinson annulation products is kind of like when we did the Diels-Alder. We wanted to stack the diene and the dienophile close together. It would draw them close enough together that when we drew the electrons moving around, they were already prearranged in that correct configuration. So I want to show you how to do that kind of prearranging your substrates, your 2 reactants, so that you get the right 6-membered ring in the Robinson annulation. So in the case of the Robinson annulation, we of course have our conjugated system, our unsaturated, in this case, ketone. Notice we have to have a ketone for this system because we're actually deprotonating this side of the ketone for the second step. Okay, so we also always have to have this conjugated ketone for the aniline, for the Robinson annulation. Okay, so the other side also is typically a mono or diketone. We can have another ketone up here. It doesn't matter. All we want to do is make sure that this is the most acidic proton because we need to deprotonate there first. We need to create the enolate out of the unconjugated form. All right. So let's take it and line it up so that anytime you can take any of these substrates, and just like with, it can be drawn anyway to start with, and we want to rearrange it such that we have it so that the double bond is on the same side as our methyl group here. So our methyl group here and our double bond have to be facing the same direction, okay? Then once we have our double bond, and it doesn't matter what our substrate is, as long as we redraw it in that configuration, right here, then we want to draw our other substrate such that the ketones are kind of pointing in the same direction, okay? So in the case here, I'm just going to draw a small ketone right here. And we want to draw it in the same direction, okay? The reason we want to do that is because this methyl or this ketone portion here on the conjugated one is going to be the one that ends up attacking the carbonyl directly. And this alpha carbon here on the ketone, the non-conjugated ketone, is the one that's going to come out and attack at that beta carbon of the unsaturated carbonyl compound, okay? So by lining them up such that you first of all, have your double bond here on the same side with your methyl portion of your ketone or your other non-conjugated portion of your ketone, and then line it up so that the carbonyl of the compound you're about to make the initial enolate out of is in the same, pointed in the same direction here. You will line it up so you always make a 6-membered ring. Okay. So just like in the case of our Diels-Alder reaction, come on, shrink, there we go, right here. Once we do our first step, which of course is the making of the enolate and forming, gosh darn it, sorry, got my foul language there. We're gonna make our enolate anion here, which is gonna be the one that reaches out here. These electrons are gonna kick in here and give up here, giving our anion. Then of course that's gonna be transferred back to the solution. We'll deprotonate here. This is going to attack this carbonyl here. So unlike a Diels-Alder that happens all at the same time, we actually have a stepwise process happening here. We're going to form our anion first, our first enolate, do our addition first, then rearrange that. Then we're going to deprotonate on our previously unsaturated system and use that to attack our first carbonyl. And then of course that gives us the alcohol. So after those first 2 steps are done, we still have our alcohol here. We've regenerated our carbonyl here, and then our remaining parts of them are over there. And then the last step is of course the heat, where our double bond will always end up in conjugation with our carbonyl compound. So another way to think about it is the conjugated carbonyl is a conjugated carbonyl in our product too. It's just the conjugation is moved over from the original 2 carbons to the new carbon-carbon bond. Okay, so questions on that? Okay, so just line them up and then make all your bonds. Okay, so the last reaction that's kind of related, it involves you making an imine like the stork, but you are doing it in a slightly different way, okay? So in the manic reaction, the key to a manic reaction is that you end up adding 1 carbon and an amino, and either a secondary amine or an amine to the system, okay? So we're actually adding a CH2 and an amine to our original carbonyl compound, okay? So the way this happens is we take formaldehyde, which is the simplest aldehyde, and we preform the formaldehyde with the amine to create that activated species that then can be attacked by the enol form of the ketone. Okay, so the first step in this is we pre-react a secondary amine with an aldehyde to form this hemiamyl compound. Okay, so it's kind of like, it's not exactly the same as the stork enamine, because you have a secondary and it gives us this intermediate compound, which gives us our iminium cation here. Okay, by resonance, this still has a partially positive charge on it, on that carbon there, but notice how we have that pre-created, that activated carbon now in that system. Okay, so in that reaction mixture, because this is done in the presence of acid, we actually have our acid interacting with our other species, in this case, our ketone. And when it does that, we have that acid catalyzed eno-keto tautomerism. And when it's in the enol form, even though it's very little of it's there, it can have that double bond act as a nucleophile and reach out and grab a hold of the partially positive carbon on the iminium cation. Okay, when it does that, what we've done now is we've created a new carbon-carbon bond. Okay, and the carbon-nitrogen bond goes from a nitrogen-carbon double bond to a single bond, and that's a stable carbon-nitrogen bond. And this carbon here is sp3 hybridized, and therefore it's no longer activated to elimination like in the imine. So the key features here are the primary portion here comes from the ketone compound. This little CH2 comes from the formaldehyde, and whatever amine you use at the end still stays attached to the compound. So the manic is kind of like mixing the stork and mixing a regular enol addition reaction together. So it's a little bit different, but it's a good way to add one CH2 and an amine functionality to a carbonyl compound. And notice you keep your carbonyl compound, in this case, a ketone. Okay, so that's the manic reaction, and that's why it's a little different, but it fits in to this chapter. The fact that we're using that enol keto tautomerism, we're using an activated carbonyl compound, and we end up building carbon-carbon bonds. Okay, so that's the last reaction we're going to talk about in chapter 19. However, I do want to go ahead and try to summarize and do a compare and contrast of the different reactions in this chapter, which will end up in my table that I'll be creating as well. Questions? Do you have other things you'd like to compare and contrast or summarize in this chapter before I go forward and do this, this other system? Okay, I'm assuming nobody's yelling at me, so we will continue. All right, so the first thing we want to look at in this chapter is the idea that we've started with everything we've done up to now. We generate an enolate, and that's the reactive species, okay? So that's chapter 18, and that summary page, actually let me pull up that summary page from, okay. Let me pull up that summary page from, where is it? Oh, it's gotta be in Acrobat. And I kind of want to walk you through the table on how to use that chapter 18 summary table and what the chapter 19 summary table will look like. All right, let me go ahead and stop sharing this one and start sharing this one right here. Okay, so you should see the chapter 18 reaction table here. Okay, can somebody chime into the group chat and say they can see that for me?
Yes, we can see it.
Okay, great. All right, and there we go. I gotta move you guys over. Okay, so the idea here is this is something what we're gonna summarize, and what I did was on purpose is I only drew the part that was changing and the part that is important, okay? So for example, if you look at this structure here, this CH2 is important because that's the proton we're pulling off. That's the acidic proton. This is the alpha carbon, okay? So that's why it's specifically drawn out. Notice in this haloform reaction, we don't care about this side of the ketone, but we must have this methyl ketone here. So that's why the structures are drawn this way. And R can be anything. It can be structures, it can be, uh-oh, it's paused. Why is it paused? Stop share, reshare. Okay, so can you see my cursor moving too?
Yes.
Okay, great. So the idea here is this is what we're starting with. This is kind of what the reagents we might be using to do this. And this is the functional group transformation going from this to this. Okay, so that's what we're looking for here. So in this particular reaction, we're looking at acid catalyzed halogenation, meaning we're going to add an halogen to this alpha carbon. We're going to take an alpha hydrogen off and add an alpha carbon. And we do that with these reagents here. So that's how to use this chart. Now, when we have acid catalyzed, you only get monosubstitution. So that's drawn out here in their conditions, or our, complications is what I like to call it sometimes. However, if we have a base catalyzed halogenation, we can do all of the alpha hydrogens right here. So we can do multiple, we can do 1, 2, as many as you have base to do it, which means if you have 3 alpha hydrogens, which is why the haloform reaction is slightly different, you actually can oxidize that off, halogenate it to make it a really good leaving group, and then it's oxidized off and you get your carboxylic acid. So really the haloform reaction is really an extension of our base catalyzed halogenation. It just went too far and hydrolyzed off a group. So that's how to use this chart to help summarize what's going on in our system here. Okay, the derivative of this is called the Hell-Vollard-Zielinski reaction, where we're getting alpha halogenation here, and we're using that halogen and a phosphorus. Okay, now if you stopped at the halogen and phosphorus, you end up with an acid halide. So the next reaction down here says without water. Notice there's water as your second step on this one. So you get you have your alpha halo acid here, but if you don't add the water, you're going to end up with these being halogens. Okay. And the other condition that allows you to do that is this one right here, where we have our thionyl chloride and our acid, or our NBS and our acid, will also generate these kind of mixed halo compounds. Okay. Then of course, if we wanted, once we form those alpha halo materials with carboxylic acids, we can attack them with different nucleophiles and generate our substituted products. These are all in this chapter. This is the alpha hydroxy, this is the alpha amino, and then this is where we can add stuff to that system. Okay. So, and this works with any electron-proton group. So this is summarizing the idea that we would have that. Now, this last reaction here, we have an E2 reaction. We haven't done this in a while, but this is actually what we call the end step of the aldol condensation, where it loses OH. It does this reaction, it can eliminate to give us this conjugated system, this alpha beta conjugated carbonyl compound. So that's how to look at that reaction there. And then the next thing we have is the decarbonylation. And remember, we have to have this acid with a beta ketone is our substrate here. And with heat and acid, we lose CO2 and we have our ketone as our product. Okay, so that's how to look at this table. And this is how I built the table to make sure that we would keep all of these things kind of in track. Okay, so when things get complicated, like in the malonic ester synthesis, let's keep track of what's happening here. We're basically doing the decarbonylation system here, but we have 2 different carboxylic acids we're adding. So our product is a carboxylic acid with whatever chain added to it. So we're going to add a CH2 plus an OH to whatever our alkyl halide is. That's what we're doing. But I did it stepwise. Notice I have product stepwise to show that if you stop at just the base and your alkyl halide, you still have your diester. If you add acid and water, then you're going to get your diacid. And then if you heat it, you get your monoacid extension. Okay. And the same thing in our next 2 reactions, where we had our acetic acid here, we always end up with adding 3 carbons. And we always end up with a methyl ketone, because it's this end of the system is where this methyl ketone comes from. So the first step is, of course, our substitution with our enolate. Second step is hydrolysis to allow us to get this 6-membered ring to allow for decarbonylation. And the third step is our final product. So that's why the malonic ester synthesis always yields a carboxylic acid, and the acetic ester one always yields a methyl ketone. And then I wanted to add the stork right here, because this kind of ties into what we did with the the iminium, the manic reaction. Notice the only reason we can't form this imine with the aldehyde is we don't have that other carbon. We cannot form the double bond to carbon here. So the double bond has to stay between what the carbonyl carbon was and our secondary amine. So in this case here, this is the actual first product form, but then once we hydrolyze it, we get our ketone back. So that's how to use this table. And that's what we're gonna do for the next half. I'm gonna stop sharing and I'm gonna share my iPad again. All right. So this same kind of summarization for chapter 19, okay? All right, first thing to remember is all Claisens use esters, okay? So that's the key, that's our first step here. So in our Claisen reaction here, we use esters. Okay, so in a simple Claisen reaction, we use the same ester as the enolate and as the attacking species, okay? So Claisen is an ester, and it always makes a beta keto ester, okay? One of the esters is turned into a ketone, one of the esters remains the ester. And the compound that remained the ester is the one you made the enolate from, okay? So that's how to remember the Claisen reaction, okay? Now, that leads us to the crossed Claisen reaction. And in the crossed Claisen reaction, you have chosen to have two different materials that you're reacting with. And in this case, you can use an ester or an acid chloride. And, okay, wait, let's actually go to the ester one first, sorry. Okay. So we've chosen our substrate, so we're still using two esters, but one of our esters has no alpha hydrogens, okay? Which means you must form the enolate from the one species, the one that has alpha hydrogens. Okay, there we go. So our enolates always form with the one with alpha hydrogens, and it always attacks the other one, okay? Which means the one without alpha hydrogens is the one that turns into the ketone, always. The one with the ester keeps the one with the alpha hydrogens remains as the ester. The one without the alpha hydrogens turns into the ketone. Cross Claisen, one has no hydrogens. They still make a beta keto ester. Okay. And then if you have two esters on the same compound, you can make a ring out of them. And that's just an intramolecular Claisen, or also called the Dieckmann, okay? And the key feature in the Dieckmann is you typically only form 5 and 6 membered rings. So you have to find which of your carbons that you can make the enolate on that will form a 5 or 6 membered ring. And we're gonna do that for tomorrow as our activity. Okay, all right. So if you don't, this is a hybrid reaction. The only difference between this and a classical Claisen is that you have an even better leaving group, okay? In this case, we have a really good leaving group in the chloride. The alkoxide is still a good leaving group because it's actually regenerated in the species. This is just an adaptation such that we can have it used for, it's still very similar to the cross Claisen in the fact that only one species had alpha hydrogens, the other species does not. Okay. Oops, not that way. Come on. There we go. Okay, so that's the Claisen. Claisens always start with esters and you always end up with beta keto esters. Okay, now in contrast, the aldol starts with aldehydes and ketones, And if you do the aldol addition, you always end up with an aldehyde and ketone and a beta alcohol, beta hydroxy compound, okay? Not until you heat it does that cause a dehydration and you form that unsaturated keto compound, okay? So you can think of the aldol as forming an aldehyde and an alcohol in there. And so you always get that beta hydroxy compound in the system. So if it's the same aldehyde right here, we'll end up with just creating that new carbon-carbon bond at the enolate site going to the other carbonyl site. The enolate site, which would be here, attacks the carbonyl site on another compound. So this was the one that was attacked by the enolate, and the one I'm circling now was attacks as the enolate. Okay, so the aldol always generates a beta hydroxy aldehyde or ketone until you heat it. Okay. So in the cross aldol system, you've done the same thing where one of your species has no alpha hydrogens. That makes sure that you know exactly which compound you made your enolate on, and therefore you'll know exactly which part is going to have the aldehyde or ketone on. Okay. So in fact, tomorrow I'm going to actually draw out the 4 products available to us here. I say on this slide here, but I don't draw it out, and I will draw that out tomorrow. I'm going to draw out the 4 products that you would get from an aldol condensation without selectively choosing your substrates. Okay. Okay, come on. There we go. Okay, so and just like with the Claisen, you can do an intramolecular aldol condensation, and it does the similar thing where you can form either a 5 or 6-membered ring. You almost never can form a 4-membered or a 7-membered ring. Always look for which way to deprotonate to give us your 5 or 6-membered ring. And remember, we have free rotation, so we got to bend those around and look at them. Just like with the Robinson annulation, pre-align it ahead of time and then draw your new bonds. Okay, now the aldol condensation follows a second step of heating to eliminate your beta hydroxy compound and give you an unsaturated alpha beta ketone or aldehyde. And once you have an unsaturated alpha beta ketone or aldehyde, you can do addition reactions on it. And that's the next step right here, is our addition reactions. Again, very strong nucleophile, you'll get attack at the carbonyl. Weak nucleophile, including enolates, you get attack at that beta carbon. And if you're attacking that beta carbon with an enolate that has a name, it's called the Michael addition. Okay. Now, the other thing to draw attention to is that once we move past aldehydes and ketones and esters, any electron withdrawing group will work. We can do it with amides, we can do it with nitriles, we can do it with these imines, we can do it with this iminium anion. The key feature is that if we have an electron withdrawing group next to an unsaturation, that will allow us to do a Michael addition. So, like I said before, one of the great substrates for the Michael addition is this nitrile compound right here. You'll see that a lot. I think there's even one in the homework. Okay, questions about summarization of chapter 19. Again, the great thing is it's all the same mechanism. Draw it on a piece of paper that Claisens are esters and give me beta keto esters. Cross Claisen, the one that was the ester with the alpha hydrogens is the one that's the ester at the end. Okay, aldol. Aldol gives you aldehyde or ketone hydroxy compounds until you heat them, and then they become unsaturated, conjugated carbonyl compounds. Once you have that unsaturated carbonyl compound, you can do addition reactions on them. Poor nucleophiles will give you addition products. Strong nucleophiles will give you addition across the carbonyl product. And then extending that to the Michael addition. Questions? I swear you're all mute. Okay, so I'm gonna go ahead and stop sharing my screen. Oh. There we go. And okay, so for tomorrow's class, I'm going to go through a compare and contrast summary of all the different reactions for these two things. And then that's going to set the stage for our activity for the second half, which will involve annulations, both Robinson and Dieckmann and intermolecular aldol. Okay. If nobody has any questions, go forth and prosper.
Thank you.
We'll see you tomorrow.